Good, it's recording now. So at the beginning of the semester, I talked about the 2's complement representation to represent signed integers. So this is the standard way of representing signed integers on computer systems. Okay, so if you look at a binary number, so the hardware does not give any meaning to the bits. So bits are just bits in the hardware. It's the software that gives meaning to these bits. So when we write the software, we give meaning to these bits. So for example, when you look at the number in binary, this number can be unsigned. You can look at it as an unsigned integer, or you can look at it as a signed integer. So, okay, so for example, if you are using 8 bits to represent a binary number, so using 8 bits, you can have 256 possible values, starting at 0, 0, 0, I mean 8 zeros. So let me use here my highlighter. So you can start at 8 zeros. So this will be the number 0. And then you can end up at 8 ones. So these are 2 to the power 8, which are 256 possible combinations, binary values. So these are 256 values in binary. Now, if you look at this number to be, so from the hardware point of view, the bits are just bits. They have no meaning. Now, if you look at these bits to be unsigned, then the decimal value will be from 0 to 255. Okay? So these numbers actually have no sign. They are unsigned, and therefore we can start at 0 and we can end up at 255. So 255 comes from the sum of the weights. So it is 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128. This will give you 255. Okay? Now, you can have a different view of the 8-bit binary number. You can say that the number is signed. So you can give a meaning to these bits. It's the software that gives a meaning to these bits. So if the number here is, so the first one, if the number is signed, you can say that half of them will be greater than or equal to 0, and the other half will be negative. So from, if the most significant bit is 0, okay, you can say that the number is positive. So it will have exactly the same unsigned value, but these are positive numbers. So you can go from 0, plus 1, plus 2, all the way to plus 127. But if the most significant bit is 1, you can say that this number is negative. And you can give a negative weight to the signed bit. So here, rather than giving a positive weight, which is 128, you can say that the signed bit, because we are dealing only with 8 bits in this example, okay, so you can say that the weight of the signed bit is negative. So here it will be negative 128. So this will be negative 128 plus zeros. So this will be minus 128. This is minus 128 plus 1. This will be minus 127. And finally, for the last number, it will be negative 128 plus 127. This will give you negative 1. So notice that negative 1 is represented as all ones in binary. So this will be the decimal value for the same bits which are in binary. So remember that the bits have no meaning in the hardware. It is us who give meaning. So you can give 2 different meanings, okay, for an 8-bit binary number as either unsigned or signed. We also have talked about sign, magnitude, or 1's complement. These are also possible, other possible representations, okay, for a signed integer. But the standard way is 2's complement. So this is why my focus here is on the 2's complement representation. But at the beginning of the semester, I also talked about sign, magnitude, and I also talked about the 1's complement representation. So now you can relate the signed and the unsigned value. So you can say that the signed value is the unsigned value minus 2 to the power n, where n here is the number of bits. So number of bits that you have in the number. So in this example, it will be 8 bits. So, for example, take this one. If you say, for example, what's the unsigned value? It is 128. Minus 256, it will give you minus 128. Or you can say, for example, look at the last one. The last one here, what is the unsigned value? It is, so for this last number here, which is all ones, what is the unsigned value? It is 255. 255 minus 2 to the power 8, because n is equal to 8. So 255 minus 256 will give you -1. So that's one way to determine the signed value from the unsigned value. Another way is to indicate that the weight of the most significant bit, this bit here, will be negative. So it will have a weight which is -128 because we are dealing with 8-bit numbers. So n here is equal to 8. So take any number in binary. If it is a signed integer in the 2's complement representation, just add the weights. And this is how you can obtain its decimal value. So it will be -128 plus 32 plus 16 plus 4 for this example, and it will be -76. Do you have any question about this? So this is how you can obtain the decimal value of a binary number when this number is represented in the 2's complement representation. Questions? If you don't raise questions, I'm going to assume that you understand the topics, and I'm going just to continue move on. Okay? So feel free to interrupt me, or you can raise your hand, and I will answer. I will address your question. So already we have seen this topic at the beginning of this semester. So I think that you understand this topic so far. I talked also about carry versus overflow. So carry is important when you are adding unsigned integers. And when you get a carry, it indicates that your unsigned sum is out of range. That's the meaning of carry. Okay? So it indicates that the sum, which is unsigned, is out of range. Okay? It exceeds the maximum that can be represented with n bits. Okay? That's the meaning of the carry. Now, overflow, on the other hand, we talk about overflow when you are dealing with signed integers. And when you have overflow, it means that your sum, which is signed, is out of range. So we don't look at the carry, we check if there is overflow. That's the meaning of overflow. It means that your signed sum is out of range. Now, this can happen if you are adding, overflow can occur if you are adding two positive integers and the sum is negative, or when you are adding two negative integers and the sum is positive. If this is the case, then we have detected overflow. There is another way to detect overflow. We say that overflow, which is represented here by V here means overflow, by taking the XOR of the last two carries, Cn-1 XOR Cn. So Cn-1 is the carry on the most significant bit, and Cn is the final output carry. So if these two carries are different, then in this case you have overflow. If these are the same, then there is no overflow. Okay. Right. So notice that overflow cannot occur if you are adding numbers of opposite sign. And if you are adding a positive to a negative or a negative to a positive, you can never have overflow. But you are adding actually two positive numbers or two negative numbers, then overflow can occur. Okay. Here are some examples of carry and overflow. So there are four cases. Either there is no carry, no overflow, or there is carry but no overflow. You might have overflow without a carry, and you can have overflow and a carry at the same point. So I have these four examples. I already talked about these examples at the beginning of the semester. So in the first example, I have the number 15 plus 8. Notice that the sum is equal to 23. Now there is no final carry. There is no carry here. And there is no overflow. So carry equal to 0, overflow equal to 0. So the sum is correct. In the second example, I have two numbers. Now the second number is interesting. This number here can be unsigned or it can be signed. If it is unsigned, it will be 248. If it is signed, it will be -8. Okay, so it can have two decimal values depending on how we interpret this number. Okay, so we can say that this number is unsigned and its decimal value is 248, or we can say that this number is signed in the 2's complement representation and its decimal value is -8. So when you are adding these two numbers, you get a final output carry, which is here. This is my final output carry. So carry is equal to 1, but there is no overflow. Overflow equal to 0. Why? Because these two carries, this one and this one, are identical. And when you XOR them, you get 0. Now notice that I'm adding, when you look at these numbers to be signed, you are adding 15 plus -8. So the sum is 7, which is correct. 15 minus 8 is 7. Notice that these two numbers are of opposite sign. One is positive, the other one is negative. So when you are adding numbers of opposite sign, you can never have overflow. Okay. So that's also something that you can always check, verify. So you can never have overflow when you are adding two numbers of opposite sign. In the third example, I have overflow, but there is no carry. Notice that in this third example, I'm adding 79 plus 64. So the first number is 79, the second number is 64. Whether you look at them as signed or unsigned, they are both positive, okay? 79 and 64. Notice that the most significant bit here is 0 and 0. This is 0, indicating that this number is positive. This is also 0. Now, when you add, you get a carry here on the most significant bit, but there is no output carry. So the output carry here is 0. So these two carries are different. So that's an indication of overflow. Now, notice that the first two numbers are positive plus positive. I expect a positive result, but it turns out that my result here is negative. So when you look at this number as signed, you get -113. If you look at it to be unsigned, it will be 143. So the correct sum of 79 plus 64 is 143. This is why, if you look at the numbers to be unsigned, we got the correct sum, which is 143. We did not really get an output carry. Okay, so this indicates that carry here equal to 0, indicating that the unsigned sum is correct, but we got overflow. So these last two carries are different. That's the meaning of overflow. And you can see that the sum is negative. It's -113. If you look at the number here to be signed, it will be -113. The last example, I have carry and I have overflow. So if you look at the first number is 218 if it is unsigned, it's -38 if it is signed. The second number can be 157 or -99. Now, when you add them, you get this number here in binary, which is 119. Now, notice that there is an output carry, which is shown here. That's actually carry is equal to 1, indicating that my unsigned sum is out of range. So 218 plus 157 should give me a number which is larger than 119. So notice that the sum is less than the input operand because the sum cannot be represented with 8 bits. I need one extra bit. So if you drop the carry and you put it here, you get 119 plus this bit, which is 256. You will get the correct sum. So you have to add plus 256. Okay, so let me just write it here with my mouse. This is 256. So if you add 119 plus 256, you get the correct sum. So the carry here, the output carry is 2 to the power 8 because we are adding 8-bit numbers. Now, if you are adding them as negative numbers, you expect that negative plus negative is equal to negative, but you are actually getting a positive result. So that's an indication of overflow. You can see there is overflow because the last two carries are different. So here we have 0. Here I have 1. So the last two carries are different. So this is an indication of overflow. Okay. Any question about this? Now we understand clearly the difference between carry and overflow. Good. Questions? تفضل حسن.
دكتور الاوفرفلو لا دائما يكون يا 0 او 1 صح؟ ما يصير 2 3.
لا ما في 2 3 يا اوفرفلو يا اما يس يا اما نو. So 1 معناتها yes there is overflow. 0 معناتها no there is no overflow. يا ما في overflow يا ما في overflow. It's not like a number. Okay. So overflow indicates yes or no. It's not okay. So overflow here, it's indication that whether we have overflow or there is no. Any other question?
Hear me?
Yes, Hussein.
دكتور الاوفرفلو بس يجي مع بس مع الساين صح؟
صحيح.
يعني اذا اخذنا الارقام انساين ما نقدر نجيب
overflow. We don't need overflow for unsigned. We just need the carry for unsigned.
Yes, okay. Thank you.
So this is the big difference between carry and overflow. So when you are dealing with signed integers, we look for overflow. We check the last two carries to detect if there is overflow or there is no overflow. If you are dealing with unsigned integers, yani if you are adding unsigned integers, then we look for the carry. If there is a carry or no carry. But if you are adding signed integers in the 2's complement representation, we check for overflow. And to detect overflow, we check the last two carries. The last two carries, this will tell us if we have overflow or there is no overflow. Or you can just inspect the numbers. And you are adding here, for example, two numbers which are negative. You expect that, for example, in the last case, the fourth case, you are adding negative plus negative, you expect the result to be negative, not positive. Okay. Right. So that's the difference. Now you can think about it differently, okay, by looking at the range. So when you are dealing with unsigned integers and your number is represented using n bits, okay, for example, in the previous slide we used 8 bits, so n was equal to 8. So if you are using n bits, n is the number of bits that you would like to use to store your number. Yani, for example, today, I don't know if you have used the C programming language, you know how to program in C. In the C language, for example, they have the type int. Int means integer, signed integer, okay? We also have the type unsigned int. And if you are programming in the C programming language, you have unsigned int and you have int. So you have two different types of integers, unsigned versus signed. So if you are dealing with unsigned integers and we are using, let us say, unsigned int, so we use n is equal to 32 bits. So each integer is going to occupy 32 bits inside the memory of a computer system. So the smallest integer will be 0 because you start at 0. And the maximum will be 2 to the power n minus 1 because you are using n bits. So in total, we have 2 to the power n values. The smallest, the minimum is 0, and the maximum is 2 to the power n minus 1. Now, if you get the sum, which is greater than the maximum, then in this case, you get the carry. See, if you are adding two unsigned integers and you get a carry which is equal to 1, that's an indication that your sum is out of range. It is greater than the maximum that can be represented with n bits. Okay. Now, if you are doing subtraction of unsigned integers and the difference turns out to be negative, negative cannot be represented as unsigned, we get a borrow. And if you use the concept of the borrow, okay, you will see actually there is a borrow in the case of subtraction. So that's an indication that your difference is negative, but there is no representation for negative if you are using unsigned integers. In the case of signed integers, you have the 0 is in the middle. If you are using n bits to represent signed integers in the 2's complement representation, you say, what's the range? So the minimum will be negative 2 to the power n minus 1. Notice it's n minus 1 here, the exponent. Because half of these values will be negative. So starting at minus 1, minus 2, minus 3, all the way to this minimum, negative 2 to the power n minus 1. And for example, if you are dealing with 8 bits, if n is equal to 8, it will be negative 2 to the power 7, okay, which is negative 128. And the maximum will be, so we have 0 in the middle, and the maximum will be 2 to the power n minus 1 minus 1. Okay, so you will start here at negative 2 to the power 7, which is negative 128. Did I say negative 120? It's negative 128. Okay, so if you have negative 2 to the power 7, let me write it down. So if n, let me write down here. So if n, probably I have it in my next slide. If n is equal to 8, so you have here minus 2 to the power 7. That's negative 128. And the maximum will be 2 to the power 7 minus 1. That's the maximum, which is 127. So you go from negative 128, that's the minimum, and the maximum is 127. It will be plus 127. That's the maximum positive. Now, if you are adding, let us say, two signed integers, which are here. So suppose that you have a number here and you would like to add it to a number here. Okay. So you are adding these two positive integers, and you get the sum is greater than the maximum. So you get the sum outside here. Then we call it positive overflow. Or you are adding two negative integers, which are here and here. Okay. Then you get a sum which is smaller than the smallest negative, smaller than the minimum negative. Then you get negative overflow. So you have overflow in these two different directions. You have positive overflow and you have negative overflow. Okay, so positive overflow, it means that your sum is greater than the maximum, and negative overflow, it means that your sum is less than the minimum. In both cases, we have overflow. Clear? Is this clear? Students, you have a question?
Yes, Doctor.
Yeah, clear.
Okay, good. Good.
Doctor?
So notice that if you are adding a positive to a negative, yani for example, if you are adding this number here plus this number here, the sum should be in the middle, in between. So therefore, you cannot really have overflow when you are adding a positive to a negative or a negative to a positive. So in this case, when you have two numbers which have opposite sign and you would like to add them, then the sum must be in the middle, and therefore you cannot really have overflow. Okay, right. So, like, how about subtraction? How do you do subtraction? Now, if you would like to compute a minus b, then you can convert subtraction into addition. Now, this is good because in order to calculate a minus b, I can say a minus b is equal to a plus the 2's complement of b. So we can convert subtraction into addition to the 2's complement. So minus b is the 2's complement of b. So we can use the same adder for addition and for subtraction. So if I would like to use the concept of the borrow, okay, like we have done at the beginning of the semester, okay, so if I would like to subtract using the concept of the borrow, the same way that we subtract in decimal, okay, you can do it different. And you can do it with the concept of the borrow. Let me use my pen tool here. So we say 1 minus 0 is equal to 1. 0 minus 1, you cannot subtract, you have to borrow. I'm showing the borrow here is negative 1 because we have to subtract it from this digit. Okay, so when you borrow, you are borrowing this 1 from here. It becomes 2 minus 1 becomes 1. Okay, so it becomes 2 minus 1, you give you 1, and then you have to remove this borrow here. So therefore, this becomes 0. When you borrow, this becomes 0. So 0 minus 0 equal to 0. 1 minus 1 equal to 0. Now here, 0 minus 1, you cannot subtract, you have to borrow. Okay, so therefore it becomes 2 minus 1, you get 1. But I cannot borrow from the 0, I have to borrow again. So therefore this becomes actually, so this becomes actually 2 minus the 1 becomes 1, minus the 1 becomes 0. And then when you borrow from this one, it becomes 0 minus 0 equal to 0 and 0 minus 0 equal to 0. So this is subtraction in binary using the concept of the borrow. Now, the textbook does not really go into these details. I'm just explaining how you can use the concept of the borrow. Now, the textbook shows you how you can use the concept of the complement, because the way that the hardware is implemented is that it does not really use the concept of the borrow. Okay, so the way that the circuit is implemented, rather than designing a special circuit, you can design a special circuit that uses the concept of the borrow for subtraction, but will not do it. Why? Because I can use the same adder to do both addition and subtraction. So why double the cost of the hardware? Why not use the same adder for doing addition and subtraction? So I can convert subtraction into addition to the 2's complement. So look at this number, take its 2's complement. So this is the 2's complement, and then add it. So basically use the same adder in the hardware But take the 2's complement. Now we know that the 2's complement is the 1's complement plus 1. I will show you how we can implement this in the hardware in a minute. So this is the 2's complement. If you add just the 2's complement, 1 plus 0 is equal to 1, 0 plus 1 is equal to 1, 1 plus 1 equal to 0, and the carry. So you have this carry plus 1, you get 0, and the carry. So the carry plus 0, you get 1, 0 plus 0 equal to 0, 1 plus 1 equal to 0, and the carry. Now notice that this carry plus 0 plus 1, 0, and the carry. There is a final carry. But is there overflow? No. There is no overflow because the last two carries are identical. So therefore, the last carry is ignored. And this is the correct sum. So if you look at these two numbers are signed, okay, the second number is a negative number. So here we are subtracting two positive numbers. This is positive minus positive. It's the same thing as positive plus negative. And you get the sum here is equal to positive. So when you convert these from binary to decimal, you can actually get their decimal values, and you can check that the subtraction was done properly. And we have converted the subtraction into addition to the 2's complement. So we have the correct result. There is no overflow. These numbers are signed. Okay. So for this reason, we ignore the overflow. Now remember that a plus the 2's complement of b. So if I would like to calculate a minus b, I will add a plus the 2's complement of b. But the 2's complement of b is 2 to the power n minus b, where n here is the number of bits. So here we have n is equal to 8 bits. So n is equal to 8. So this is a minus b. It's the same result as a minus b, but you will get 2 to the power n. And this 2 to the power n here is the final carry. So for this reason, we ignore this final carry. Now, as long as we don't really have overflow, this final carry has no importance. Okay, we can simply discard it. That's it. So it's not important. And my correct sum is represented using 8 bits. So 8 bits, this is my correct sum, and it is positive. Okay, in this example, sometimes you might get a negative result. Okay. So that actually is how we can convert subtraction into addition. Is this clear?
Doctor?
Yes.
We will always have no overflow when we convert, right?
No. Sometimes you can actually get overflow. In this example, we did not really get overflow.
And what happens when we have overflow?
I mean here, because we are adding a positive to a negative, you will not get overflow. But sometimes if you are, for example, adding a negative to a negative, you might actually get overflow. Or adding a positive to a positive, you might actually get overflow. So there are cases in which you can get overflow. So what you care is that these last two carries, whether they are identical or different. So in this example, they were identical, indicating that there is no overflow. But you have to check if there is overflow or there is no overflow. So if there is no overflow, then basically your result is correct. And notice that it's exactly the same result if you do it with the concept of the borrow. And if you don't use the 2's complement representation, if you just subtract them using the concept of the borrow, the same thing that we subtract decimal numbers using the concept of the borrow, you will get exactly the same result. But we prefer to do addition to the 2's complement because it's easier to design the hardware this way. To design this, you use the same adder in the hardware to do addition and subtraction, and therefore reduce the cost of the hardware. Okay, is this clear?
Okay, it's clear.
So we need the carry here to detect if there is overflow or there is no overflow. But if there is no overflow, we can simply discard the carry completely. The final output carry, we don't really need it. And the final sum can be represented in 8 bits. However, if you are dealing with unsigned integers, this is why I need to stress. If you are dealing with unsigned integers, the carry is important, okay, for unsigned integers. And you might actually have, the question might depend on the question, is that to have the carry as part of your sum, because sometimes they might ask you for the exact sum. So therefore, sometimes you have to use the carry as part of the sum and increase the number of bits from 8 bits to 9 bits by having the carry. But here we cannot actually increase it to 9 bits. The sum is 8 bits, and it is it's correct. Okay, it's a correct result, and there is no overflow. Right. So let me show you how we can design a circuit. So I can have an n-bit adder. We have seen the design of an adder before. So that's my n-bit adder. So this consists of n bits. So if I'm going to implement it as a ripple carry adder, so this will actually consist of n full adders inside, and therefore we have to propagate the carry from one full adder to the next full adder. Okay. So this adder is capable of adding n bits. So here I'm using a bit vector, which is used in Verilog. Have you seen bit vectors in Verilog? Have you seen that in the lab? Students, have you seen bit vectors?
Not yet.
No.
Okay, right. Let me explain it briefly. So this actually A consists of n bits and B consists of n bits. So I can say that n minus 1 down to 0. So this n minus 1, this is the index of the most significant bit, and 0 is the index of the least significant bit. So it means that A consists of n bits. So notice that I'm putting here n, and I'm drawing here on the arrow indicating that this is not just a single bit, it's actually n bits. So this is, in drawing, people actually use this to indicate that my input A consists of n bits, and it is a bit vector, okay? It's called a bit vector. The same thing for B. So I would like to add n bits plus n bits, okay? Now, in the case of addition, I'm going to use an n-bit adder. So basically, I'm going to use n full adders, if this were a ripple carry adder, and propagate the carry, okay, from one full adder to the next full adder. Okay, so let me put here, okay, carry propagation. You see that how the carry is propagated without going into the. So this box here is a ripple carry adder, which is capable of adding n bits. Let me just clean up this. So this is my n-bit adder, which consists of n bits, okay, n full adders. Now, it's going to produce a final sum that consists of n bits. Notice that here my sum is also a bit vector. Notice that here n indicating that we have n wires, not just a single wire, but n wires, okay? The same thing here, we have n wires. Now, this is my input B. Now, notice that this is XOR gate, but this is not just one XOR gate because it receives here n inputs, so we have n wires. So this is not just one gate, this is n XOR gates. Okay, so we have one XOR gate for each bit. So if you have, for example, 8 bits, we will have them bit 7 down to 0. Okay, so if n is equal to 8, we go 7 down to 0. If n is equal to 16, we go 15 down to 0. Okay, that indicates how many bits I have in B. Okay, so that's my bit vector. So here n will indicate that how many wires and how many gates I have. So by drawing here a XOR gate, it means that, and we have n, okay, wires at its input, it means that this XOR gate is replicated n times. So these are n XOR gates. Now, the reason why I have this XOR gate, it depends on the operation, on the up. Up here is my operation. So 0 means add, and 1 means subtract. It is just a single wire, which I'm showing it in red. If I would like to add, I'm going to XOR every bit of B with 0. So add will be 0. So therefore, the output of this XOR gate, or these n XOR gates, will be B. Let me just use I cannot write with my mouse, so I have to use my pen tool. So let me just write here B. So you can see that if my operation is add, okay, 0, it means addition, then the output of these n XOR gates will be B, right? So basically, my input here will be A, which is added with B, and C0 is just equal to 0. This C0 here will be 0, right? If the up equal to 0, so the input will be 0. So the output will be A plus B. So the sum here will be A plus B. طبعا plus the carry in C0 equal to 0. So basically it will be just A plus B. That will be the sum. So that's in the case of addition. In the case of subtraction, up is equal to 1. That's in the case of subtraction. So we use up is equal to 1. So when this up is equal to 1, rather than having here B, it will be B prime. Okay, because when I XOR B with 1, I'm going to XOR every bit of B because I have n XOR gates. So when you XOR it with 1, if you have a 0, it becomes a 1. If you have a 1, it becomes 0. So basically, you get the complement of B. That would be the 1's complement of B. So I'm calling it B prime. So every bit in this bit vector is XORed with 1, and therefore we get its complement. It's 1's complement. And we make C0 not equal to 0, but equal to 1 in the case of subtraction. So rather than using 0, we use 1. So rather than calculating A plus B in the case, so A plus B in the case of addition, in the case of subtraction, we calculate here A plus B prime plus 1. What is B prime plus 1? Students, what is B prime plus 1? B prime is the 1's complement, but B prime plus 1 is equal to what?
2's complement.
2's complement, yes, thank you. And what is A plus B prime plus 1?
A minus B.
Exactly. So I use the same adder to do subtraction without the need to design a different circuit for subtraction. The same adder is doing addition and subtraction. Is this clear? Is this clear? Do you have any question about this? So I use the same adder for doing addition and subtraction. The trick was in the input B. I can pass B to my adder and C0 equal to 0. That will be addition. Or I can pass B prime by XORing it with the operation. So when I XOR with the operation, when I XOR with 1, all the bits of B. With 1, I get B prime. I get the 1's complement of B. And then I make C0 equal to 1. That's my input carry. So it will be A plus B prime plus 1. It's A plus the 2's complement of B, which is A minus B. Okay? So this will actually calculate A minus B. So I'm using the same circuit to do addition and subtraction. And I can control it. I can control it with this up. So this wire here, which is up, if it is 0, I will do addition. And if it is 1, I'm going to do subtraction. Clear? Nice, right? So this way, I don't need to have 2 circuits, one for addition and one for subtraction. I can use the same circuit for addition and subtraction. You see now how engineers think, okay? Reduce the cost of the hardware. And use the same hardware actually to do 2 things. Use the same adder to do subtraction. Okay, good. So this is my last slide in this presentation. It seems that you don't really have any question. Everything seems to be good. If you have no question, I will continue at my same rate. If you want to pause me. Okay. Let us see actually how good you are. I'm going to create a new slide here. Let me just erase this and erase this. This is an empty slide. Okay, can you see this empty slide? And let me use my pen tool. I'm going to write here. Okay, I'm going to write a 4-bit number. Okay, 1 0 1 0. Now, if this number was unsigned, what will be its decimal value? So what is the decimal value of this unsigned number? 10. And this is signed. So what is the unsigned value of 1010?
10.
Thank you. Let us make it more. Okay, yeah, 10. Let us just write 10. Okay. Go on. This is in binary. This is in decimal. If it were signed 1010, what will be its decimal value?
-6.
-6.
Thank you. It's -8 plus 2 is equal to -6. So you have two possible values, either 10 or -6. صح? You agree?
Yes.
Right. Suppose I would like to extend this number, extended from 4 bits to 6 bits. So let us do here. Okay, if it were unsigned, how do I extend it?
Just add 2 zeros.
To the left.
Yes.
You have to add 2 zeros to the left or to the right?
To the left.
To the left, yes, thank you. You have to be clear about your answer. So it will be 0, 0, 1, 0, 1, 0. So this will also be equal to 10. But this will be 6 bits, right? Let us extend it to 8 bits. So how do you extend it to 8 bits?
Add 2 zeros to the left also.
Thank you. Okay. This is still equal to 10. Did we change anything?
No.
This is called what? Zero extension. This is known as zero extension. When do we use zero extension? When the number is unsigned. Right. If the number is signed, how do I extend it from 4 bits to 6 bits?
Now the most significant should be 1.
So what should be the number?
With 6 bits or 8?
Yes, 6 bits. What should be the number in 6 bits? I would like to extend this to 6 bits. But now my number is signed. So extend it to 6 bits. Please do it quickly. We don't really have the time. So how are you going to extend it to 6 bits? Can you put 2 zeros to the left?
Yeah.
No.
Why not?
Put 2 ones.
We put 2 ones. Why?
First,
Okay. Yes.
We check the sign bit. So we actually put 2 ones. And then we write here 1, 0, 1, 0. What is the decimal value of this number?
-6.
-6.
It is still -6, yes. It has not changed. So this is called what? Sign extension. Now look at the decimal value. This one here is what? Is -32 plus 16 plus 10. If you add them up, you get -6. Do you agree? This is 16. This is the 10. Go on, it's actually 8 plus 2. Okay? Right. So do you have any question about this? Students, do you have any question about this? Right, if I would like to extend to 8 bits, how do I write it?
Another
Add 2
2
ones to
ones.
the left.
Yes. So it will be 1, 1, 1, 1, 1, 0, 1, 0, right? So the sign bit is replicated here 4 times. So what is the value of this number converted from binary to decimal if it were signed?
-6.
-6.
-6. It has not changed. So this is called what? sign extension. This is called sign extension. So if the number is unsigned, we use zero extension. We use zero extension if the number is unsigned to extend the number. If the number was signed, we use sign extension. We cannot use unsigned. We cannot really use zero. We have to use sign extension. So we extend according to the sign bit. If the sign bit is 1, we extend it with ones. If the sign bit is 0, we extend with zeros. Is this clear? Is this clear, students? Is this clear?
Yes.
Okay, good. So now you understand the difference between signed and unsigned integers, and you understand the difference between zero extension and sign extension. Hassan, tfadal.
Doctor, is the leftmost digit in the signed integer always become negative?
Is it always what? Sorry?
Is it always negative?
If the sign bit is 1, it means the number is negative. If the sign bit is 0, it means that the number is positive. Yani you can actually have a positive signed integer. Yani for example, if you look at this number here, 0, 1, 1, 0. What is this number? This is in binary. What's its decimal value?
6.
Plus 6. So it's a positive. See, if I would like to extend it, okay, from 4 bits to 6 bits, I have to extend according to the sign. So if the sign is 0, you extend it with zeros to the left. If the sign bit is 1, you extend it with ones to the left. So we call this sign extension. Extend according to the sign bit. Is this clear?
Yes, doctor, but what I mean is, if we have, for example, 3 digits number.
3 digits.
110.
Okay, 110.
This one is negative here.
So then in this case, your n is restricted to only 3 bits. So if I have the number 110, okay, let me discard this. So if n is equal to 110, this would be my last example. So if n is equal to 3 bits, and the number is 110 in binary, okay, what will be its decimal value? If it were signed, if it were unsigned, it will be what? It will be 6. But if it was actually signed, so this will be unsigned.
Minus 2?
Yes, it will be -2. That will be the signed value. In fact, if you have only 3 bits, what will be the range? If it were unsigned, it will be from 0 to 7. If it were signed, that will be the unsigned range. You can only represent numbers from 0 to 7 if you are using only 3 bits. If you would like to find the signed range, when n is equal to 3, what will be the signed range?
-7 to 6.
Minus
8.
Minus.
From -8.
-7.
Wrong. -4 to +3. -2 to the power 2, 2 plus 2 to the power 2 minus 1. Because you have n is equal to 3 bits. So you go here -2 to the power 2, 2 plus 2 to the power 2 minus 1. So this is -4, this is +3. This is the range. So you have -4, you have -3, -2, all the way here to, okay, +3. You understand? So these are the 8 values.
It is 3 bits, not 2.
3 bits, yes, 3 bits, not 2. You can represent 8 values. 4 of them are negative, and 4 of them are greater than or equal to 0. So the exponent is negative 2 to the power 2 to plus 2 to the power 2 minus 1. So from minus 4 to plus 3, you have 8 values. Because you have only 3 bits, you have 8 values. 4 of them are negative, and 4 of them are greater than or equal to 0. Clear? That's it for today. Thank you very much. Let me stop recording.